Now that we know how to interpret complex exponentials, let's actually solve a differential equation where the characteristic equation has complex conjugate roots. So here's such a differential equation. A second derivative of y minus 2 times first derivative of y plus 5y equals 0. So we can translate this into a characteristic equation. Remember, the order of the derivative turns into the power of m. So we get m squared minus 2m plus 5 equals 0. If you try to factor this, you'll find it doesn't factor using real numbers, but you can always find roots for this equation by using the quadratic formula. So m is going to be, let's see, 2 plus or minus the square root of 2 squared minus 2 squared, I guess, 4 minus 4 times 1 times 5 is 20, all over 2 times 1, so that's 2. So let's simplify this mess. We get 2 plus or minus the square root of negative 16. So we are going to get complex solutions here. So let's see, 2 plus or minus a square root of negative 16 is 4i over 2. So this is going to be 1 plus or minus 2i. All right. So our solutions to the differential equation are y1 equals, so remember how this works is the real part of your complex conjugate pair becomes the real exponential. So this 1 gets multiplies right there, so e to the 1 times x times cosine of, and then the coefficient on your imaginary part, not the I itself, just the real multiplier here, becomes the multiplier in your trig function, or in your sine and your cosine, so 2 times x. And then the same thing, but with sine, so y sub 2 is e to the 1 times x, so e to the x, times sine of 2x. I won't calculate the Wronskian of these two, but the Wronskian does come out to be 0, so these two are linearly independent. So we have a fundamental set of solutions for our second order equation, so we can write the general solution to the second order homogeneous equation. It's any constant times the y sub 1, which is e to the x cosine 2x, plus any real constant, c sub 2, times y sub 2, e to the x sine 2x. So you can see that once you've done the hard work of interpreting what complex exponentials actually mean, in the context of a repeated root characteristic equation, once you have the complex conjugate roots, writing down the solutions to your differential equation is actually pretty straightforward. You just drop the real part in over here and the complex part in there. Or I'm sorry, the imaginary part inside your trig function there. Let's look at a special example of this sort of differential equation. So for this particular differential equation, what makes this special is that there's no dy dx term in here. Right? So that means its coefficient is actually 0. So when we translate this differential equation into its characteristic equation, we get m squared plus 16 equals 0. And we can solve this. Either you could use the quadratic formula, but since there's no m term in this, you could move the 16 over. So m squared is minus 16, and then take square roots. So m is plus or minus the square root of negative 16, and the square root of negative 16 it's a complex number, but it's actually purely imaginary, so plus or minus 4i. So in this case where there's no first derivative term in the original differential equation, the roots to the characteristic equation are purely imaginary. And when we use this to write down the solutions to the differential equation, right, we still get two linearly independent solutions to the differential equation. And we get e to the, well now remember it's the real part of m goes right here to multiply x, but the real part of m up here is actually 0. There is no real part. So we get a 0 right there, times cosine of 4 times x. And then for y sub 2, we get e to the 0x times sine of 4 times x. So for both of these, for y1 and y2, the real exponential part just disappears because e to the 0 is 1. So we get cosine 4x for y1, and for y2, we get sine 4x. So there's sort of a nice symmetry here. When your characteristic equation has complex roots, the real part always becomes an exponential, and the imaginary part always becomes sines and cosines. And that's true even if there is no real part, then you just get sines and cosines. And if there's no imaginary part, then you just get exponentials, and that's the distinct real root case. So really the only outlier to this whole thing is the repeated real root case.